Hello, my dear students. Welcome you all to Sri Jayendra Rank Zone classes. I am your mentor and your friend for the subject chemistry, and I will be dealing with organic chemistry. My dear students, I'm going to start with optical isomerism. We have already started with optical isomerism. Today, our topic is diastereomers. Starting with diastereomers, what are diastereomers? These are the stereomers which are non-superimposable. These are stereoisomers which are non-superimposable and do not bear mirror image relationship and do not bear mirror image relationship. Understood? And they are non-superimposable, but they do not have the mirror image configurations. For example, a compound having two asymmetric carbon atoms having two asymmetric carbon atoms a compound having two asymmetric carbon atoms can have four stereoisomers can have four stereoisomers can have four stereoisomers as shown below in the case of tartaric acid. In case of tartaric acid. Understood? So this is one pair of enantiomers you can see. In the same, we can draw a second pair of enantiomers. You can see these two are the mirror images. Now, the same example. These are also mirror images. So first and second and third and fourth are mirror images of each other. The four isomers are basically, this is the second pair of enantiomer. So if we compare the first one and the third one, this is the first one, okay? And this is the third one. If we compare the first one and the third one, they are neither superimposable nor they are mirror images. They are neither superimposable nor they are mirror images. So that is why in the definition I have mentioned that they are non-superimposable, but they are not mirror images. And these non-superimposable non-mirror images are known as what? Diastereomers. First and fourth are also diastereomers. Okay. As second and third and second and fourth. Okay. They are also diastereomers. Now, what are the characteristics of diastereomers? They show similar, they show similar but not identical chemical properties. The rate of reaction of their chemical kinetics, the rate kinetics are different. They show different reaction kinetics. Means the rate of reactions is different. They have different physical properties such as melting point, boiling point, densities. Different. Such as melting point, boiling point, densities, solubilities, refractive index. Okay. They can be easily separated through fractional crystallization. They can be easily separated through fractional crystallization, fractional distillation, chromatography. Okay. Diastereomers are also encountered in the case of geometrical isomers. They are also shown by geometrical isomers. Okay. Like this is cis form, this is trans form. So both are non-superimposable, non-mirror images. Okay. Next is meso compound. The compounds containing two or more chiral centers two or more chiral centers, but possessing achiral molecular structure, but the whole structure is achiral. Achiral molecular structure. Because of having the elements of symmetry, means the plane of symmetry, plane of symmetry, and they are called meso compounds. So these compounds, they have plane of symmetry, and that is why, okay, the whole structure is achiral, but they have two or more chiral centers. Okay. For example, this carbon and this carbon, they are chiral centers, but this is the plane of symmetry. You can see, okay. Plane of symmetry. So plane of symmetry makes these molecules what we can say achiral. Okay. Now they are optically inactive, means they cannot rotate the plane of the polarized light. Cannot rotate the plane of polarized light. Okay. They show internal compensation. Their optical activity shows internal compensation. Internal compensation means the half rotation goes clockwise, half rotation goes anti-clockwise. So overall rotation results 0, anti-clockwise. Okay, that is why the overall rotation comes to be 0. Now, the cancellation of rotation is known as internal compensation. In short, the meso compounds are optically inactive due to internal compensation. I have already told you. Now I'm going to talk about why we call these optical isomers the configurational isomers. Okay. Configuration, it can be defined as the three-dimensional arrangement of groups around chiral center around chiral center. There are two methods for assigning configuration to a molecule. One is the relative method. Relative method. and another one is absolute method. So first we are going to talk about the relative method. Relative method use D, L system, that capital D and capital L should not be confused with dextro and levo. Okay. Basically, it uses as the commonest sugar a kind of trio sugar glyceraldehyde as a base. Okay. So it uses D-glyceraldehyde and L-glyceraldehyde as the basis of classification. As the basis for their configuration determination. Okay. Now, in the relative method, D refers to the arrangement in which the OH group attached to the stereo center stereo center is on the right side of the Fisher projection. We have already discussed about the Fisher projection. Right side of the Fisher projection. Whereas L refers to same, the OH group attached to the chiral center on the left side. Okay, like now please remember which chiral center we have to use. We have to use that chiral center which is nearest to this CH2OH. So this is only the chiral center here. OH is on the right side. This is capital D. OH on the left side. This is capital L. Okay, understood? This method was found for the study of optically active sugars, used for the study of optically active sugars, as the sugars are defined as polyhydroxyaldehydes and ketones. Defined as polyhydroxy. They are the polyhydroxy derivatives of aldehydes or ketones. Understood? Glyceraldehyde also contains hydroxy and aldehyde groups, but this method cannot be used for those molecules which do not possess hydroxy aldehyde groups, like cannot be used for the compounds not having CHO and OH groups. For example, CFCl BRI, FCl BRI. We cannot use the D and L configuration for this compound. Okay. In case if there are two or more than two OH groups are present, two or more than two OH groups are present, then the DLN configuration is decided on the basis of OH group of the lowest chiral. Okay. In the golden rule, following Fisher projection. Ethyl so this is D form. Okay. So they have hydroxy group attached to the carboxylic acid. Okay. This one and this one, the lowest chiral, the OH is attached on the right side. This is also D form. Okay. The same this is the L form. Understood? Wait. So this is the L form. Okay. So this is the relative configuration, the D form and the L form. Okay. Now, what is golden rule? Usually the Fisher projection is drawn so that the longest carbon chain in the molecule is vertical the longest carbon chain in the molecule should be vertical with the highly oxidized functional groups at the top. With the highly oxidized functional group at the top. Like for example, here COH is on the top Okay, so this is on the top, this is at the bottom. The longest carbon chain is taken vertical. Okay, and this is the lowest chiral center. The OH is on the right side. It becomes the D4. Okay. Now comes the RNS system or absolute configuration. R means rectus, means right, and S means sinister, that is left. R and S nomenclature is assigned as follows. Step 1. By the set of sequence rule, we give the priority order of the atom. Give the priority order of atom or group connected through the chiral carbon. Okay, so by the set of sequence rule, the priority order of atom or group connected to the chiral center is given. Step 2. If atom or group of minimum priority present on the vertical line, then you have to see if the movement of i's in clockwise direction, then it is R. If the movement of i's in anti-clockwise direction, then it is S. Okay. Movement of i's taken from 1 to 2, 2 to 3 through lower molecular weight group if needed. For example, now see, this is the Fisher projection. 1, 2, 3, 4. Understood? So, if you can see, we are moving from 1 to 2, 2 to 3, 3 to 4. So, it is basically coming as R, means the movement is clockwise. And if, according to the priority rules, okay, the group is 1, 3, 2, 4. Okay, so if we have to move from 1 to 2, to 1 to 2 means anti-clockwise, we are moving this side. Okay, so this is basically S, anti-clockwise. Okay, now step 3 says always take that the minimum priority group or atom should be always present on the vertical line. Okay, if minimum priority group is present on the horizontal line, on horizontal line. Then we have to just do vice versa, means clockwise is S and anti-clockwise is R. Okay, like this is what the horizontal line, 3, 2, 4. This is R clockwise, anti-clockwise, sorry, anti-clockwise. Okay, some common examples: COH, CH3, H, OH. Understood? Now, sequence rule we have already done. Okay, the sequence rule says the atom which is attached to the chiral center is be taken into consideration. Here, the most prior group is, okay, what we can see, the most prior group is this one, then two, then three, and then four. Okay, so we are moving, we have to 1 to 2, that is anti-clockwise. Okay, so it is R form, because the reason is that the minimum priority group is present on the horizontal line. Okay, the minimum priority group is present on the horizontal line, and that is why we are considering anti-clockwise as R and clockwise as S. There's one more example. So this is 1, this is 2, this is 3, and this is 4. The minimum priority is on the horizontal line. Okay, here is from 1 to 2, it is clockwise, means it is S form, R form, S form. Okay, now we will talk about the optical isomerism in compound containing no chiral carbon atom. Containing no chiral carbon atom. Okay, there are many compounds belonging to the group of alkenes, okay, dienes, cycloalkanes, pyro, and biphenyls, okay, which are not having chiral carbon atom but they show optical isomerism. For example, first we are talking about allenes. Like C double bond C double bond C. This is the general formula. Okay. They basically have even number of double bonds. Even number of double bonds exhibiting optical isomerism. Provided that two groups attach to each terminal carbon atom. two groups attached to each terminal carbon atom. Okay, each terminal carbon atom. Okay, or we can make it like this. Now, even number of double bonds, they exhibit optical isomerism provided the two groups attached to each terminal carbon atom. Okay, either in this pattern or in this pattern. Alkylidene or cycloalkanes and spirocompounds. They also show when one or both of the double bonds in allenes are replaced by one and two rings. When one or both of the double bonds in allenes are replaced by one and two rings. One or two rings. The resulting systems are known as alkylidene cycloalkanes or spirenes. Alkylidene cycloalkanes or spirenes. For example, this is 1-methyl cyclohexylidene 4-acetic acid. Okay, or basically it is written as C B CH2 CH2 C CH2 CH2 C A B. Okay, these are spirenes. So when one or both of the double bonds, if they are replaced by one or two rings, the resulting systems are respectively known as alkylidene cycloalkane. This is spirene and this is alkylidene cycloalkane. They also show optical isomerism. Biphenyls. Substituted diphenyls are also divide of the individual chiral carbon atom, but the molecules are chiral. Carbon atom, but the molecules are chiral. due to restricted rotation. Due to restricted rotation. Okay, around the single bond between the two benzene nuclei. Between two benzene nuclei, and hence they must exist in two non-superimposable mirror images of each other. Superimposable mirror images of each other. Okay. Okay. So it is an example of biphenyl. Now to find out the number of optical isomers, when the molecule is unsymmetrical, it cannot be divided into two equal halves. The number of D and L isomers is 2 to the power n. Number of mesoforms 0. Total number of optical isomers 2 to the power n, where n is the number of chiral carbon atoms. Carbon atoms. Okay. For example, so here you can see there are two chiral carbon atoms. Okay. D and L isomer, that is 4. Okay. There is no plane of symmetry because we are having one C2H5 and one CH3. They cannot be divided into two equal halves. Number of D and L isomers 2 to the power n 4. Okay. When the molecule is unsymmetrical and the number of chiral carbon is even, n are even. Number of D and L forms 2 to the power n minus 1. Number of mesoform 2 की power n by 2 minus 1. Okay. Total number is equal to addition of the above. That is 2 की power n minus 1 plus 2 की power n by 2 minus 1. For example, tartaric acid. So even number of chiral carbons. Okay. But here the molecule is can be divided into two equal halves. Okay. So number of D and L forms 2 की power n minus 1. You can calculate. That is 2. Number of mesoforms 2 की power 2 by 2 minus 1. That is 2 की power 0. That is 1 because we have one plane of symmetry over here. Okay. If the molecule is symmetrical, number of D and L form 2 की power n minus 1 minus 2 की power n by 2 minus 1 by 2. Okay. Number of mesoform 2 की power n by 2 minus 1 by 2. Total number of isomers 2 की power n minus 1. So these are about the diastereomers. Then the optical isomerism shown by the compounds not having chiral carbon. Okay. So this is all about, and we have to discuss the Reslin mixture, resolution, and that's it. They are the last topics. Okay. So if we talk about the Reslin mixture, what is Reslin mixture? Okay. It is an equimolar mixture of a pair of enantiomers mixture of a pair of enantiomers okay. It is optically inactive. They are optically inactive because they show external compensation. External compensation simply means what? That the equimolar mixture of enantiomeric pairs enantiomeric pairs the rotation caused by the molecule of one enantiomer is cancelled by the other enantiomer. The rotation caused by the molecule of one enantiomer is cancelled by another enantiomer. Okay. Represented by D and L both or plus minus. Racemization. It is the process of conversion of an optically active compound into a racemic modification. Conversion of optically active compound into the racemic modification. Into the racemic modification. Under the influence of the agents like heat, light, chemical agents. Okay. There is another term, resolution. It is the process of separation of constituent enantiomeric form. Process of separation of enantiomeric forms from a mixture. Okay, from the racemic mixture. So my dear student, that is all for optical isomerism, I think. Okay. Now what we have to do, what you have to do, we have to just practice maximum number of questions. Okay, so that we can come across. There are many concepts which can only be learned by solving the problems. Okay. So I'll take your leave. Till then, bye bye. Take care. Stay safe. Stay healthy.